So we're already at lecture 4, and last week we covered everything about ANOVA, ANCOVA, MANOVA, and those type variants, also things which you might have seen in your undergraduate, and now we're straying more and more into the deeper end, into things you might not have seen, like logistic regression. Sorry. Grab a seat. So part of this will be things you should also be aware or should have also covered in your undergraduate, which is correlation. Like you hopefully have heard of Pearson correlation, perhaps also Spearman correlation. You might have also heard of ordinary least squares regression, and you might have done some of those. Any of you are completely unfamiliar with regression, you've got no regression whatsoever. And then the new bit might be logistic regression. Not sure if you covered that, but so logistic regression is regression with a dichotomous outcome, with something which can only take two values. And so that will be the new bit today, and coming weeks we'll start adding new techniques which you might not have covered in undergraduates. So the pace will keep up. So I would continue to encourage you to work on the exercises, post questions in this question board. I'll do my best to respond as fast as possible. I'll do my best to give you feedback as possible via the solutions you get to view, so you can check your own results and see if you're going in a good direction. Also, it's time to start thinking and working about your assignment. I think after today, you could cover nearly all of it except for the moderation bit. So there's really no excuse to not be working on your assignment also alongside, because you have all the tools from the slides and the exercise to do so. Again, there's nothing out of the ordinary in there, in the sense that most of it is things which either will have been covered in class or in the exercise you've been asked to make, where you can then check what the result is like. So there's nothing. So don't be. I think it's just a matter of sitting down and finding the time. I know you're all very busy, but it's just a matter of finding the time and doing it. Any questions on the process thus far on things? Yeah.
When's the assignment due?
What the assignment due? If I'm not, I'm unlucky. It's on my birthday, if I'm not mistaken. So it's Friday, the 17th of November, for assignment 1. But double check that on Blackboard, and I'll also update that. But it's not finalized. So in case you were worrying, yeah.
Is that the second assignment, like the same kind of thing?
Yes, but then on the second part, so I haven't posted it yet because it'll be about the second half of the lectures. So and you have until January to cover that. So that will go online soon after the first assignments, also to give me some type of leeway, perhaps, to adjust some things. So mostly, I think it will be online shortly thereafter. And so it's again based on the lectures and the class, but then we'll be doing more advanced things like factor analysis, structured equation modeling, multi-level models, and your second assignment is all about that. And it's shorter, if I'm not mistaken. So it's different techniques. Okay. So last week, ANOVA, ANCOVA, today, correlation and regression, and also this logistic regression, which you might have come across. So I hope that by the end of the day, you know a little bit more about correlation or ordinary least squares regression. You know a little bit more about the assumptions about regression, which you might have heard also. We've talked about homogeneity of variance. Might have also heard of homoskedasticity, yeah. So those type of terms are things which will pop up again, and then we'll talk a little bit about logistic regression, which is regression when you have a dichotomous outcome. And again, I have only a limited amount of time, so you have to read by yourself. I've given you a very large reading list. I've given you references, so it's really for you to make most of it. And I'll do the highlights here, and I'll show you how to do the techniques. But if you want to find out all the formula and maths, I don't have time to cover that. I also don't think necessarily that's always useful, but they're there if you want to find them out. So for the assignments after today, you should be able to complete the following sections: correlation, or ordinary squares regression and the testing of assumptions, plots associated. So you've also done some plots already, like making scatter plots. So that's similar to what you would do in this exercise and also in class, and a bit about logistic regression, which is towards the end of the first assignment. So, correlation, you might have used correlation as well, and mostly it's the first step. So you want to find out if there's some type of association between variables. So usually it's not the end result in which you end up with your thesis, but usually it's the first step, and you might have built these large correlation matrices to explore where there are associations and which variables might be related to one another. Yeah. And you may want to find out the strength of an association if it exists. So that's the purpose of doing correlations. So if you want to find out the formula, I've listed them here, but the key thing to bear in mind is it's covariance, so the degree to which x and y overlap, which is the covariance measure divided by the pooled variance measure by the geometric mean of the variances. So that's the formula. So that's the really ugly full-blown maths, but you should remember it as covariance over the square root of variance x times variance y. Yeah. So that's so it's the covariance divided by the geometric mean of variances, and you can read back on your notes, or you can check the mathematical derivation on the link I give you. So if you want to find out more, there's assumptions associated with correlation, not necessarily with the correlation coefficient itself, but especially with the significance testing associated with correlation. So we're dealing with continuous variables. So if you have an ordinal variable, you can't use correlations, Pearson correlations. You would have to use an ordinal measure, right? So the key exception here is dichotomous variables like gender, for example. You might have seen in a correlation matrix because they're 0, 1. And so they're treated as being continuous variables for mathematical purposes. So dichotomous, occasionally you will see correlation matrices with dichotomous variables in there, and that's the exception to the rule, so to speak. But if your variable is of an ordinal level, so if it's a lot to frequent, and it only has 4 categories, then you shouldn't be using Pearson correlation coefficients. Everybody understands why this is the case? Yeah, it's because we're working with means and we're working with covariance and variances, and we can't really calculate those for ordinal measures. Yeah. So the other assumption is normality. Again, the central limit here term comes to the rescue here. So the larger the sample, the less you have to be concerned about this. But you should be aware, for example, outliers. Think back of the graph with Anscombe's quartet and the data Soros. So these were all similar type of correlation coefficients, but in one case it was driven by a single point. And if you would have not plotted your data, you would have assumed that's a very strong relationship. The correlation is 0.81, but it's entirely driven by that one point. If you take away that point, the relationship falls flat. So it's good to always not just rely on the summary statistics or the correlations, but to also plot your data and see what it looks like. Because again, underneath that correlation coefficient can be a parabola, like a curvilinear linear relationship. It could be this type of a linear relationship with an outlier, or it could be like completely dichotomous, like it could be completely just 2 groups driving that correlation coefficient. Yeah. So everybody understands why that's important to do. So always plot your data. So the other thing you might have heard of is homoscedasticity. We'll return to that later when we talk about regression. So basically, it's the notion that the error should be constant as we progress along x or y. So we should we'll discuss it when we come to regression. But you shouldn't be seeing a funnel where the errors become wider or smaller, or the residuals, because residuals are sort of the trash bag of your regression, and you want them to be fairly constant, because that means we're making the same type of error at the beginning of the curve, so to speak, as towards the end of the curve. Otherwise, we might be over or underestimating our relationship as the errors go up or go down as a function of x. Does that make sense? Linearity, so that's also a thing back of Anscombe's quartet. It can't be a parabola, it can't be a curvilinear relationship. To some degree, that's tied into the normal distribution, which you also expect. So think back to those. And a particular pet peeve of mine is population versus sample correlation coefficients. So that if you sample the entire, so suppose you want to calculate a correlation between one trait and another trait. If you sampled everybody, then there is no probability. The correlation coefficient of the sample is that of the population. So suppose I'm interested in finding out the relationship between height and leg lengths and all the men of Amsterdam. After I've sampled the last man in Amsterdam, I know what the association is. There's no need to calculate any test statistics because I've emptied the pool of the group I want to make inferences about. So what you often see, for example, is that people take all the countries of the world and then plot a correlation coefficient and add a significance test to it. That makes little sense because if you've had all the countries of the world, there is no probability. It is the relationship that you find. Unless you find new countries somewhere magically appearing, they can't appear. And so after that pool is empty, you can't really do any more. Yeah. So that's something, a particular pet peeve of mine, and why I've written it. So don't make that mistake ever. So if you've sampled all the students which exist, all the year 1 students, for example, then and your goal is to infer to year 1 students, then there is no statistical inference, because it is the relationship that we find. That's different for experiments, because experiments, in principle, we can put more and more people to the experiments and randomly allocate them than for samples from correlations, for example. Yeah. So after I've sampled the last country or monkey or student or something, the pool is empty, and we can't really do any type of statistical inference. And you can read more. I've written about this if you get really bored. The other thing important to bear in mind is that correlation is not causation. That's probably been repeated to death to you also. That you need to do experiments and causally manipulate the variable you're interested in, and so that you find the correlation. It doesn't necessarily establish causation, but usually it's the use. There's no association, then usually it rules out the existence of a causation. So that's why we're interested in correlation coefficients. And in some cases, you won't be able to do experiments because it's unethical, or you're unable to do this, and you're just left with observational statistics. Now, I can't go into too much detail, but there's some really clever work from computing science, which actually shows that in some cases, from correlations, you can derive causation. And they've done some really clever simulations, for example, to find out you have cases where we know what the causal association is. For example, the size of the room and the amount of rent it's worth. So you sort of know which one determines the other one. And the sense that if you put in some additional money, suddenly the room doesn't magically grow. It's the size of the room which determines the amount being asked in terms of rent. And so what they found is that the error in the error distribution, so if the error of x can influence the error of y, that might tell us that there is a causal relationship. And so this is frontline stuff, but they claim that based on correlational associations, they're able to infer causality. Not always, but in cases where it exists, and where it's predetermined, for example, in the case of rent or in some other phenomena where we know it exists, and they validated these techniques. And that's because you can make assumptions about if x is causally related to y, then x can influence the errors of y, but y cannot influence the errors of x. And by doing lots of simulations with computers and machine learning, you can find out the direction of the relationship that way. So that's so perhaps in the future this will be revised, and people will say, actually, with correlation we can do causation if we just have lots and lots of these cases and lots of numbers we can infer. But for now, correlation is not causation. And you should do experiments if you want to make causal claims. Okay. So how do we go about and do correlations in R? So you might have been familiar by now with the iris data set, which you might have used for your assignment also. So it's in data sets I've just loaded. It's also part of the base R, so you might not have to require data sets, but just in case I did require data sets. Also, because if it's already loaded, you might not have to name it, but I think it's usually safe to name objects. So I said iris is iris, and this is the correlation of the first column with the second column. Yeah. So by now you should know the square brackets denote positions, and what we can do then is that sepal length correlates with sepal width at minus 0.00 minus 0.117, and then the rest around. Yeah? So that's how you do correlation, but it doesn't have our p-values, or it doesn't have our test statistics. We'll come to that in a bit. So that's just, and the reason that's the case is because often you want to make lots of correlations, and you don't necessarily want all the significance tests, but you want to use those correlations as input for other models or for factor analysis or some other things. So that's why R by default doesn't give you significance. So that's another way of doing it. We can also directly, by now you should also know, you can directly call variable columns by the $sign. So if you do iris sepal length, iris sepal width, that should give us the same result, and it does in this case. Yeah. So we can also change the methods, and that's just that. So by default, it will be Pearson's correlation, but sometimes you want ordinal correlations. You might have heard of Spearman-Rho and Kendall's tau or Kendall's correlation. So if your supervisor asks you for those correlations, it's by changing the methods this way. And so just method is Kendall, and it's important that again R is quite sensitive. So if you put Kendall with a large K, it won't run it. So it's and so if you forget an L, it won't run it. So it's quite tricky that way. So if we do that, we get an ordinal correlation, and that ordinal correlation in this case is weaker than the other one. So ordinal correlations don't make the same parametric assumptions, but they might have some restraints in the sense that some of them don't really go to 1. And again, you can read more about Kendall and Spearman's correlations in the notes and in your reference, and perhaps you have to go back. But if you have ordinal measures, that's the way to use those. Now, how do we get our significance tests? So we can also use core.test, and then we use the same type of dollar notation. Again, you could have used the square brackets to denote things. And we can specify confidence levels for our significance, as you've seen, for example, with bootstrapping and some other things. So in some cases in your assignment, or your supervisor might ask you for a 99% confidence interval instead of a 95%, or for a 90% or an 89%. To some degree, these numbers are arbitrary. It's because in the Fisher and settled on 5%, and that's why we stuck with 5%. But if you like 89%, you do 89% confidence intervals. So what you then have here is it will print, it's a Pearson's product moment correlation. It will print the t-value, which you should remember from SPSS that there's a t-value attached to it. It will print the degrees of freedom. It will print the p-value attached to it. It will say what the alternative hypothesis is. So you can even, I haven't listed this here, but sometimes you might want to do, very rarely you might want to do directional testing, and you might want to do a one-tail test. So the correlation is always positive or always negative because you have a priori hypothesis as to why it should be positive or negative. In that case, sometimes it might be allowed to half your p-value, so to speak, and to do one-tail testing versus two-tail testing. Everybody understands what one-tail testing is versus two-tail testing? If I'm going too fast, also let me know. And so what is printed here is the 90% confidence interval of this, and you can see it overlaps with 0. So that's also why it's not significant in terms of the 5%. And it's printed the same value, and this is the same value which we saw in the previous slides. So if you need the full shebang, not just the actual correlation value, you can use core.test. Okay. So again, what would you write up in your report? You would write the Pearson correlation between sepal length and sepal width was not significant, and then you would write R, degrees of freedom, this is rounded to 2 decimals. Sometimes it's 3 decimals, but it's important to be consistent throughout your paper. It varies sometimes, but I usually go for 2 decimals for correlation coefficients, and then the p-value. And again, you should go back to the APA manual. I don't always publish in ABA journals, but your supervisors might, and they might care about it. So, and also for the assignments, pay attention to style. So, and you've given examples in the sense that it should be italicized, and you should list the degrees of freedom, and that's the format. And you should have done that also for your bachelor thesis and for your assignments before, in terms of APA type of write-ups. Yeah. Sometimes people would also mention the strength of the correlation coefficient. So this would be a weak to non-existent correlation, but you might recall that they're moderate to strong type of things. And sometimes people would also mention the sign, whether it's positive or negative in that description. But because it's not significant, it doesn't make much sense to elaborate here. We can make a pretty chart, and by now you should be able to do that also because you've done that you've done scatter plots before. The only thing which I've done here is I've added geom jitter, and geom jitter allows you to, so sometimes you'll have overlapping points, and geom jitter will shuffle them slightly away so they don't all overlap, because otherwise it's quite hard to see the points. That's what geom jitter does. And so it's the same type of things you've seen before. So I load ggplot to, I load ggteams to make it prettier afterwards. I load our color brewer because I want some pretty colors. And then it's ggplot. I tell it where the data is. I tell it which variables are going to be the aesthetics, so x and y. I tell it what type of color it should use. I tell it that we want to jitter the points. That's the plus geom jitter. I tell it we want to spread it out across grids because I think it will look nicer. So that's the facet grid type of command. We want the line going through it, and LM means linear model, so it's a linear line. You might have also come across Loess, which was the smoothing function you saw before. But in this case, because we're doing correlations, we want a straight line going through it. We ask you to pick some colors via scale color brewer, and we say that's the palette you have to pick from. You can have a look, so there's set 1, set 2, other type of colors which you might like. You can specify your own different colors. There's color charts. We could have an entire lecture on just coloring our charts, but you can find out more there. These are the labels which we want to add, so the X and Y label, and that's the title we want to add. And then I pick a team, and I think the tufted team is quite nice and clean. In your assignment, you'll be asked to use different teams, and you also in the exercises you've been asked to use different teams. So have a look. Some of them will do the annoying thing where they remove all the elements, and so then you might run into things that you have to first. If you put that one at the end, it will scrape all the labels because the theme is that there are no labels, and then you might run into things where you have to first run that and then add the labels to it. So that might happen in some cases. So have a look, but usually that's the issue you might have with teams cleaning up, or the fact that it's not intermediately stored, or that you're trying to save it and we'll go back to the base chart. And what you should get is something like this, which is quite nice. So you can see with colors, the species, and it's made of grids. Let's put the names of the species there. We could have done more things. We could have played around with these axes still a little bit. We could have played around with those axes to reduce sort of the white space if we want. But all in all, that's a pretty nice chart showing the association within those three species. Yeah. Any questions? So by now you should be able to comfortably make these type of charts. So practice, and every single time also in exercise, I'll ask you to make some charts. Now, often we don't just settle on one correlation. We want a whole host of correlations, so we build a correlation matrix. And again, we can quite nicely rely on APA tables to help us here. So I made something new here, which is chord table, and I wanted to make a correlation matrix for the entire data frame without species. And the reason we don't want species is because it's a multinomial or a multi-categorical variable, so it has these three cases, so we can't really use that in a sensible way for making our correlation. So that's why I removed it from the data frame. So you would make, if you want to make a correlation table, you would select all the continuous variables, or all, if in case you're doing Spearman or Kendall, all the ordinal measures which you want to use. So make sure there's no ID variables in there, or no so. And by now you should also know that you can use dplyr selects to remove variables, or to select subsets from data. And I've done it here via minus, but you should also remember you can specify the column names. You can use the column to say from this to this row. So toy around with it, and then using the apa.chordtable command. So we say this is the data frame it has to use, and we say file name correlations. So you have to give it a file name, and it will make a Word document for us directly, which again is quite nice. So again, hopefully you're getting more and more convinced that it will save you time also when you have to do lots of things for your assignments. I'll show you in a moment what it looks like in Word, but this is what it will print is the means and standard deviation, and then an APA-style correlation matrix with the strength of the correlation. So that's the minus 0.12, which we remember from being reported earlier, and the square brackets are the 95% confidence interval, and it uses a star annotation to say which ones are significant. So again, perhaps a great time saver if you have to make lots of tables and do things. Let me just see if I can show you what it looks like in a Word document, so that you can see. So correlations iris. It's a little bit large, so let me just zoom that down. So that's the type of table you would get out of it. That's quite nice. So it's printed. The means and standard deviation is correctly italicized. It's done this with a number notation. So again, you would normally waste quite some time making lots of charts, and hopefully, I can convince you that it's not all bad, and that in the long run, if you learn this, it will save you time doing this. Yeah. And so again, it will print these things, and you can edit these out before, and it will say what the values in square brackets are. They're in a 95% confidence interval for each correlation, and it's the plausible range. It will even explain what a confidence interval is in this case. Yeah. But beware. So there should be no categorical variables in there, and there should be. And if you make it very large, then it won't fit in the page. There's some ways around it, so you can specify which type of shape it should be, but don't make it too large because it will overrun and then won't look as nice. Okay. Back to the slides. So that's just to show you that it works, and you can get a Word document out of it. Now, what you could also do is you could make a nice matrix out of this. And so there's GG chord plot, which is something else than ggplot2, but it uses the same language as ggplot2. And so we have to make a correlation matrix first, and we do that via the core command and the core. So we can do that, we can feed variables to it, but we can also say, take this entire data frame and calculate every single correlation between it. And that's via the same type of core command which you had before. So we made a correlation matrix, which we're then going to feed to GG chord plot. This tells us what the order is, and it tells us whether we want to lower. Otherwise, it would have flipped it and would have done the a higher rectangle, because a correlation matrix will be symmetrical, and you'll have one on the row, but you'll have the exact mirror on the opposite. And so it's basically telling it to use only one half and to use only the lower or the upper. And what it's done here is it's printed in terms of our core. Again, that's the minus 0.12. And so it's a visual representation, and the strength of the cores gives you the strength of the association. And I think that could be quite nice, perhaps even clearer sometimes than having a table. And especially if you have lots of variables, then this might be the route to go, because then you can show all of them, and then the bright colors will stand out, and that will say these are really strong associations, and that will help you. And so a lap is just saying that it should print labels. You can also tell it to hyperlabels. So again, there's many different options and functions, and you can find out more when you read the manual for GG chord plot, but that's sort of what it does. Other packages exist which also do correlation plots, and for further info, so at the end I have a tutorial which you can look at, which will also do it, and you can also look at chord plot, which also does correlation plots, but not in a GG type of way. So now we're going to go and do one interactive thing, and then we're going to continue with the rest. So time for new data, perhaps. So we're going to use a little bit of the prestige data. It's in the car package, and you can load it via this way. So you should first install the car package in case you haven't done that, and then you can add it that way. It's just so prestige, car prestige, and then I'll tell you in a moment what it's all about. So if you haven't installed it yet. And CAR stands for Companion to Applied Regression, I think. So it's a package with lots of tools for regression and also some data sets. And so the prestige, in case it's capitalized, so yeah, you have to install the package first. You can't find it, but there was one for week 2. There wasn't one for week 3. So because we always use the same thing. Sorry, I should have made it clear.
Are we to start a new window on this, or are we to continue from?
It's what you want. Like if you think it's, I think I would recommend that you perhaps take a new one. But it's
so it won't link to any of the data previous way.
No, we're going to use new data today. Okay. again, you should notice that there will be some conflict. So recode is a command which also is used by dplyr. So bear in mind that if you load a car package and you use the recode commands, you need to call dplyr directly or need to call car directly because both of them have recode commands. So it's always good to pay attention to this type of warnings or conflicts which are load. And sometimes when you run into issues, it's because R doesn't really know whether it should call recode from car or recode from dplyr. And you saw me using the double colons to directly talk to dplyr and say, dplyr use mutate. So sometimes your code can be resolved by doing that, by telling the package directly to use that. Okay. So what is it about? It has data on prestige, of course. So it's the average prestige rate. So back in the day, sociologists rated lots of occupations and they assigned them prestige scores. And interestingly, they can relate to many different things, like what determines prestige. Is it education? Is it income? Is it whether it's a feminized profession? So perhaps nurses used to be a very prestigious job, but then as more and more became feminized, it might have dropped in prestige. So that's the type of questions sociologists are interested in, and perhaps also psychologists is trying to understand shifts in the prestige scores, and that's what this data is all about. It has a code for a census, and it has a type. So that's whether it's professional or managerial, so white collar, blue collar, or it's missing. Yeah, so you might already have some intuitions that white collar jobs might have higher prestige scores than blue collar jobs. Yeah, and so that's the type of data we're gonna work with for today. So what I would like to do is, after you've done loading the prestige data set, is make a correlation matrix with all the continuous variables. So use filter as I've done to remove variables which are not continuous from the data matrix, and then either export a correlation matrix as I've done for APA tables, or make a plot. So do one or the other. You don't have to do both, but just have a go at slimming down your data set and then making a correlation matrix, which you export either as a table or plot.